Hello, in today's videos I'm going to explain a little about the format of sorry, the format of the LVM data produced by the data reduction. So the what we name the LVMS frames is in the current format. And for doing so, I'm going to use one of the notebooks that are included in the LVM DAP. That is a notebook that basically is to visualize this data produced by the data reduction pipeline. And I hope that this will help to understand not only the format, but how to work with it in the case that you want to use your own analysis tool, but also to visualize what's the content and basically how to handle the data. Because it's the data that the DAP is going to analyze. I mean, it's a native format. So for doing so, we are going to go to the installation we did in the previous. I have made a copy of the full directory, not to modify the installation. Obviously, you don't need to do that. You can copy the notebooks in a separate directory or at your convenience. It's just for saving space, but that was easier for me. And in the DAP, in the LVM DAP installation, there is a directory named notebooks. In here, there is a series of files of IPython notebooks. The one that we are going to explore today is this one, LVMView-SFrame. I think it's self-defining. So it's the visualization tool for the S-frame format of the file. Remember that yesterday we ran the script for making a fitting, and we download one of the example frame. Now you can download any other frame. You can download, for instance, and that I think would be a good idea to download the Helix frame that it's in here. That this is the one that we have distributed in the data release 19. Let's see if I find it. Okay, go to the local volume mapper, and this is the Helix Nebula frame. Well, that's some tutorials that overlap with that, and the frame can be downloaded here. So let's download that. I have already downloaded it, so I can copy to the directory I want. So actually, I didn't need to download again, but I think that for the purpose of this tutorial, it's relevant to see where to find it. Let me. Okay, so I'm going to copy that file. So I'm going to stop the downloading. And I'm going to place in the same directory I used before. I think it's the convenient place for storing that. Just to continue with the tutorial, and then we will continue the tutorial with the public accessible data. Let's see. Well, okay, so now the file download the it's in here. Okay, this is the file that we have distributed with the data release 19. So it's publicly accessible to anyone. Okay, so for running the notebooks, in this particular one, we need the ipywidget. So this is a library that allows you to create interactive plots inside a notebook. And since I installed this from zero, as I showed in the previous videos, I realized that I need to install first Jupyter. I did not even have Jupyter. I mean, that's a new account in this environment. So you need to install the Jupyter to run the notebooks. And the second thing you need to install is this library. That is the one that allows you to open widgets that allows you to create interactive plots under Jupyter. So once you have installed that, then you just need to run the Jupyter notebook. It's going to open Mozilla Firefox in my case, but that depends on your installation. So of course, you can use Visual Studio to run all these notebooks. That's not the difference in there. So I'm going to open that, and well, we just need to go through the installation here. The notebook, and sorry. We need to tell where to find the data. So you need to modify this directory for the current directory that you have in your own installation. And for all frames that we distribute have the same format. It's basically LVMSFrame and then an ID of the tile. So this is the way that we construct the names in here. So we are going to give this LVM ID that is 004297. Okay, there is a zero missing. Obviously, you can modify that to read any other S-frame that you have modified, combined, or whatever. As far as it has the same format, there is no big difference. And what I'm doing here is just to open an HDU with this frame. And also I extract the position table with this routine. That is one routine included in the DAP tools of the LVM DAP package. So if I run that, it's going to show me the info of the file. So this is the format that is produced by the data reduction pipeline, and it will be explained in forthcoming article, I guess. So there is a primary, there's a multiple extension file that is quite usual nowadays, the FITS file. The first extension is just a header where it's all the information of pointing and telescopes and all the usual information about the site and so on. And then we have a series of files. The first six extensions correspond to raw stack spectra, RSCCs. That's it's an image where each row correspond to a spectra that it's corresponding to a certain fiber in either in the sky or a calibration, in this case in the sky, that came from each of the 4 telescopes, depending on if it's a fiber that is pointing to the science bundle, or to the two skies, or to a calibration telescope or calibration fiber. So we have the first extension is the flux, and the usual units. This 10 to the minus 15. That's that correct? I need to check that. I already put in the code. So what the DAP does when it import is just multiply that for 10 to the minus 16. So I guess it's 10 to the minus 16. But then I will check that for giving the right number. I mean, it's in the header, so we can check later on. Actually, we should check that. So let's just not to say something that is not correct. No. HU. Would be F unit or unit. Let's see if it's unit of units. 1 second, so I can check that. No, the units are in ergs. It's P unit. Okay. Okay. What's so why so extension 1, I guess. No. Why is that? But it's there has no attribute header. What? Oh, it's saying me that. That's this is weird. I'm pretty sure that it's Earth, but okay. That's really weird. Because it's uh, what I'm writing wrong. Something I typed something wrong. That's by sure. Oh, okay. So this is the unit. So you sorry for the confusion. I don't know what I was typing wrong. Doesn't matter. So basically, the units in the flux, and of course in the other extension, in the other extension, it's is the same. It's ergens per astron per second per centimeter to the square. So as I told you, the DAP works in units of 10 to the minus 16. So when you see the outputs of the DAP, you have to multiply everything to 10 to the minus 16 of this unit to have the right numbers. It's a convenient. It's described obviously in the article. So the first extension is the spectra. So we can obviously let's add a new so I don't know. We can insert the content. Okay. I mean, that's not the best way to visualize that. So x-axis is wavelength and the y-axis is the number of fibers, and it's in the inverse way that they usually, that's the way that this is plot. So we can put that lower. I think it's that way. So it's reverse, upside down. So I don't know why it's taking a while. No. So, well, okay. So that's the content of the image, and we can make a zoom. Does not allow me to make a zoom. Yeah, here. Of course, this is pretty slow. That's the interactive part. So we can zoom in, and the contrast is not the best. So let's work a bit on that. So let's see if we can make a b equal to -1 to I don't know, existing to the b max. I'm just guessing. 100. Of course, we can make some statistics and so on, but that's not. Okay, now we see something here. Okay, so this it's as I told you, it's rho corresponds to a spectra. That's not the wavelength. This is the ID of the pixels, and these are the mask regions that correspond to some issues with the columns in the CCDs, and these other ones correspond most probably to cosmic rays. And when you have a high intensity, normally this is a star in the field or something with high intensity. Well, there's not too much to say in this regard, because that's um, well, here we have certainly that's an emission line. Let's see if we can identify some emission line, just visualizing it. That was here. Here there are some emission lines, here there are some emission lines, so H alpha should be around here. So if we make a zoom, you can see the high intensity of a certain emission line, I don't know which emission line is by now. That's the reason of creating a visualization tool. That's a very poor way of visualizing the data. But anyway, this is the content of the first extension. That's another emission line. And this that's a doublet. I don't know which one it is, but okay. Anyway, so first extension is the flux intensity. The second extension is the inverse of the variance. So the error associated to this flux will be 1 divided by the root square of this parameter. And then, so that's this is the usual format that has been adopted for Sloan data for long. By the way, the wavelength is sampled in a linear way. In the tradition of Sloan was to sample in logarithm scale, but here is sample in a linear scale. The third extension is the mask. So it's 1 in these locations where you should not use the data and 0 where you should use it. The fourth is the wavelength solution. So basically how to transform the pixel, so the association of it's a pixel with a certain wavelength. It's a bit redundant in this regard because the step is linear. So with the usual work coordinate system, the shear ball and Sittelt should be sufficient, but this is prepared just in case that we have a different sampling, either logarithm or whatever. And we can visualize how is this sampling in a very simple way. We can plot plot HDU. Of course, you can use the name also, so we can say wave and without looking to the index of data. If we plot nope. Why? I didn't like it. So it has no, it's my mouse. No. Why is doing that? No. It's still showing the previous figure. It has to do with the ipywidget thing. Let's see. Clean that. No. Well, things that happen. It's just right. So I don't know why it does not likes to show me what I intend to do. Let's see. The axis object. Okay, so let's do in the classical way. So okay, finally. So this is in the x-axis is the pixel, scale, okay? And in the y-axis, let's show that. Something that we can visualize more easily. That's not a good value. Okay. So in the x-axis, sorry. Okay, so this is the correspondence of angstroms to pixels. So this is the wavelength range covered by the LVM, and this is a pixel in the x-axis of any of the row stack spectra included in here, the flux, the E-bar, also the mask. So if we want to visualize one spectra, one individual spectra, a possible way to do that could be to it cannot paste and copy in this way. We should just better copy cell below, and we should do something like that. We should plot this against HDU flux, that data of whatever, I know, the pixel, I mean, let's see the fiber E5. I'm going to name E5. That's okay. E5 equal to 10, for instance. And now the x-axis will be wavelength and the y-axis will be flux. And this is the content of the spectra corresponding to fiber 10. I don't know if it's a science fiber or sky fiber. I think that it's a science fiber, a sky fiber. We will see later on how to identify that. Okay. So in here you can visualize what is the content of each of the extensions. We can also show the content of the E-bar of the same fiber, plot in the same way, but the inverse of the variance says little. If you want to visualize the error, it's 1 divided by that to the root square. Okay. And that's the error associated with this particular fiber. And of course, you can visualize a detail. For instance, around H alpha. So now we are working in wavelength, so we can set a certain wavelength regime, and so you can see. Of course, since this is interactive, we can easily go and see that's the error, and this is the signal. That's should be oxygen 1, I guess. And I don't know. That's that to me. This is that's something that related to sky. There are pretty low signal on signs. So I don't know what correspond to a fiber 10. So maybe fiber 10 was not a good idea. I selected that randomly. I don't know, 100. That's doesn't doesn't seem to improve too much. So I have a bad luck selecting fibers. Okay, now that's a fiber where we have science data. So this is nitrogens and the H alpha. Okay, so that's H alpha and the two nitrogens. Good. Well, obviously, to go fiber by fiber in this way is not a very convenient way of visualizing the content of this file. Although scientifically will be the way to go through. So, hey, what happened with my notebook? It's disappear. Why is doing that? Maybe due to the square. Let's save it. Well, that's something with my computer that is going pretty slow. Let's came back to the info. So this is the flux content, the inverse of the variance content, the mask with a wavelength solution. This is the dispersion in kilometers per second of the line of sight velocity. I'm pretty sure it's in velocities per second. So let's be totally sure about that. So uh, sorry, no, it's in angstroms. Okay, no, but it's the coordinates of the y, the x-axis. The y-axis, there should be a unit here. Is the full height maximum in angstroms, okay, of the line of sight velocity distribution. So that this is basically the full height maximum of corresponding to the spectral resolution along the wavelength. Since we have three different spectral arms and different in three different spectrographs, we will have a different wavelength solution, and we have also a different instrumental resolution for each fiber, also projected in the. It's also when you project that in the CCD, you slightly modify the line of sight, the velocity distribution in the case of the instrumental one, and therefore for each fiber we will have a different solution, and that's why this is a raw stack spectra. It's an image. For each spectra you will have a different resolution. So let's visualize that. That's the extension. Oh, well, okay, that's not a good idea. I want to plot everything. So this is, that's not flux. This is will be fully the maximum in angstroms. Okay. And you clearly identify the three arms. This is the blue arm, the red arm, infrared arm. And as you can see, there is a considerable change in the resolution. And let's try to plot two different fibers. Like, I don't know, that's plus 10. Just to show you how this may change from fiber to fiber. So it does not only change from spectrograph to spectrograph, but also to fiber to fiber. So the DAP takes into account that instrumental resolution, and for the velocity dispersions, there is a column provided that it's the velocity dispersion in angstroms, but it's also the velocity dispersion in kilometers per second, and the 1 in kilometers per second has been already subtracted this instrumental resolution. So again, that could be quite instructive of what is the content of the LVMSFrame, but that's not very helpful to make a first visualization on the data. I mean, there are other two extensions. This is the sky frame that has been subtracted, and the sky variance, and the sky has been subtracted, created from well, actually it's a quite complex way, because we have two sky telescopes, one pointing far away in a apparently dark area, and another more nearby, and there is a way that these two information are combined and create a single frame that is extrapolated to each different fiber. That's are details in the data reduction that may change with time, but in case that you want to recover what sky was subtracted for purposes of trying to identify faint emission line, faint features that may be affected by sky, this has been stored in this frame. And finally, we have the slit map. The slit map basically is the mapping of each spectra that we have in this row stack spectra with the original fiber. So in this slit map, it's stored if this fiber corresponds to the science fiber in the central bundle, calibration fiber, the sky fiber, and so on. So that's a critical information, and to visualize the data, although we have one, and also it's included the quality of these fibers. If the fiber is broken, and should be masked, and how to assign that to science or not science. So this is the content of this table. It's a fits table, and the fibers that we are interested on are the ones that are labeled as science. Okay, so they are these ones. From them are the ones that we are going to do science. So that's basically the way to extract them is to create this mask, and you mask the rest, because the rest is not useful for doing science. So we are going to visualize the data in a two-dimensional way, and also exploring individual spectra. So what we do is to create, and because it's convenient for us, creating an extension that it's including a new extension to the already existing ones, that it basically contains the errors. That is basically 1 divided by the root square of the invariance, the I bar, sorry. And just to check that we have created that, I visualize that just to be sure. So now we create an environment for ipywidget. That's some kind of a bit of style. And this script in here allows you to visualize the frame that we have loaded in a more convenient way, I think, to basically explore the individual spectra. So since this is an interactive thing, we can create inline inputs. The first one, it's basically, so in here we have the entries, and here we have a visualization of the science frames projected in the sky, and that's the radiation and declination, and that's not a continuing interpolated, an interpolated image. They're individual it's a scatter plot. So they are the individual fibers are in here. And if I move the mouse here, clicking with the central button on, it's going to show here in the right the actual spectra corresponding to each position. Okay. The image that is shown here corresponds to a wavelength range that it's controlled by this tool here. Okay, so let's see if we find a convenient one. So of course, when it goes through something that is masked, then we have an issue. So let's see. Sorry. Let's try to select a regime that is, you can select a regime also in here. That's the plot spectral range, and it control the flux intensity that you are plotting in units of 10 to the minus 16. Okay. So in here you see that it's changing the scaling, and this is the wavelength range. Now is the full wavelength range, but we can narrow the wavelength range to something that is more convenient to identify some useful emission line, like for instance H alpha. Okay, and that's control the flux regime in here. So that's not a good idea. Let's control that a bit. So this should be H alpha. So if we go in here, like in there, if you move with the central mouse button, you create some kind of a narrow band image, okay? But we want to narrow even more. If we want to create a more narrow, it's pretty slow. Every time you move the mouse with the central mouse click on, it's creating an image. Okay, this is an image of nitrogen. Of course, this is an area that is crossing a mask region. Let's narrow down a bit more the wavelength range. So we are pretty sure this is H alpha, and this is -1. That's not allowed to have a negative thing. So let's try to make, if you want to create a very narrow image, you have to click the left mouse button to select the left end of the wavelength regime, and the right mouse button to select the right end of the wavelength regime. So this will be a narrowband image of H alpha. We have to change the flux intensity by a lot if we want to visualize that in a convenient way. And as you can see, there is not easy way to graph all the scaling intensities that are found in this nebula. Well, you can graph in here and chain, okay? So that allows you to visualize. Let's see if we have a better scale in sulfur. Okay, this is a sulfur map, and in sulfur we can scale that and see the typical ring structure of this nebula. Of course, you can also change that to a different, more convenient for you. Depends on each person. That you may like another different color map. That all the color maps included in the matplotlib distribution are going to be included here. Okay. So, for instance, nitrogen. That's a nitrogen map. Okay. And okay, so what's the advantage of this method? If you want to have a first impression, or you want to look for certain emission lines, then it's more convenient to operate in this way. And every time that you click in here, it's going to show you which spectra are you looking to, so you can recover that information. You can visualize individual spectra, or you can co-add different spectra. So instead of clicking in the central mouse button, you click to the left mouse button, you are co-adding spectra. And here we have graph and a spectra of a star, clearly seen in there. Okay, that's a field star, fits in front of behind the nebula, and that's the way to select a group of individual spectra. If you click with the right mouse button, you are removing that selection. So let's see if we select, for instance, some kind of a pseudo slit. So we move through, clicking with the left mouse button and moving through, and that could be some kind of a pseudo slit spectra across the nebula. That will be useful. For instance, you want to compare with previous data, or you want to select just a particular region, you can select that. You can save in a file, in a snap of that thing. But you can also, the previous selection, well, that's saving, okay? You can use the selected files that they are stored in this variable that is named self fiber, and from that variable that store all the fibers that you have selected. This is the ID of the fibers that you have selected that correspond to this pseudo slit that you see here. You can store that in a frame. Well, error. Why? Okay, yeah, because there is no this directory. That's a very simple thing to solve. Instead of that directory does not exist. So we need to select the directory where we have stored the data. And e what samples data, I think it's that way. No, why? Let's see what's the director code. There's a subdirectory missing. Nope. Why? No such file or directory. Examples. LVMDAP. Samples. Oh no. Sorry. I'm so used to write manga everywhere. That's my error. LVMDAP. Okay. So now in this directory there, okay, you in that directory, you're going to have this frame where you're basically have stored the selection that you have made in a fits file. So imagine that you are interested in certain objects, like certain stars or certain region. You want to make a quick analysis to have a guess of what you have in data. You can select these particular regions instead of running an analysis tool through all the data in a frame. You can conveniently select the regions of your interest. For instance, let's make something a bit practical. Let's see if I want to select. Let's remove all this. I think should be a button for cleaning all the selection. That's not very convenient to do by hand. Imagine that we want to explore 4363. That's a weak line 40. Yeah, that's the wavelength range. And we are going to change the flux intensity by a lot. Okay. So now we can explore in here 43. And let's see if we can see something here. Well, unfortunately, I remember this line is not a good line for making this test because we have all these broken things. Okay, so let's remove all this and let's look for another one. Remove it. Just becoming slow. Remove them. I don't want you to remove. Let's look for 5. 5525. Well, it's still doing. That's the bad thing of these tools is that it requires it's all the time having a memory of what you have done before. So it's plotting and plotting and plotting in a loop until all the clicks that you had done are fulfilled. So that's a complicated thing. So it's still showing the incurrent wavelength range, as you can see here. Okay. Now it has collapsed a little. So I'm going to rerun this. That's very simple. You start from 0. How you try to switch off and on again. So let's try again to see if we can select. Whoop. That's where this has gone. Okay. Let's try to select a wavelength range with 4. Yeah, very low signal to noise. So I want that. Oops, jumps. So So which line is this one? This is wavelength 40. The wavelength range. It jumps again. It's my mouse. It's not working very well. So this is 4752. That's a weak line. It's, okay, my mouse is jumping. That's nothing to do with the tool. It's my mouse. No, that's not the line. The line that we are interested on should be this one. Okay? This is the line that we're interested in. This is, you see the wavelength in here. Sorry for the mouse. It's doing funny things. Again. Anyway, this is 4755. That's Aurora line. And you can explore in here different intensity levels of these Aurora lines. I imagine that you want to run a test with whatever tool for this particular region here that you know that you have detected that line. So then you make this slit, pseudo slit map. So this is what it's going to show here. And now with the selection, you can store and make your own analysis, integrated only the regions where you have a detection, visual detection of that line, something like that. And well, of course, this tool is just for visualizing things and for understanding what's the content of the LVMSFrame. I hope that this could be useful for you, just to have a visual inspection of your data. Sorry for the confusions in some of the steps, but I think this is illustrative that this is not some kind of an over-prepared video. Is just what the kind of analysis that you usually do, and with the kind of problems that you may encounter when you do it. So, well, that's all for today. I guess that afterwards you know a bit more. After this video, you know a bit more about the format of the LVM data. And how this is created. Of course, the code is here, so you can you can inspect and reuse the parts of the code that you want for plotting any wavelength range or whatever. And the most important thing is that that's in the left is just a scatter plot of flux intensity that is created in a certain narrow wavelength range using the slit map information that is transferred to a position table in the sky. So there's no magic in there, okay? But you can explore the notebook and freely use. I mean, that's why we distribute them for your own purposes. So I'm going to stop the video of today here. It's a bit longer than I anticipated, but I hope it will be useful for you.